we want to discuss a particular set of numbers, the Stirling numbers, which play a role in combinatorics. First, we define falling factorials. Which we'll denote by x with an index n, just x times x minus 1, x minus 2, etc., all the way up to x minus n plus 1. Moreover, for n equals 0, we'll define this to be 1. This is the definition of a falling factorial. And then we get to our first definition of the Stirling numbers. There are two classes of Stirling numbers. And one tells us how we go from one basis of the polynomials in X to another basis of the polynomials in X. We define the first kind of Stirling numbers, S1, as the change of basis from polynomials which are just monomials, x to some power k, to the basis of falling factorials. And then vice versa. The Stirling numbers of the second kind tell us how to do the reverse change of basis. From the falling factorials to the monomials. Since this is a basis change, these two transformations are inverse transformations. Moreover, one can notice that they are, in some sense, lower triangular. And then if we compute some practical consequences of the fact that they are inverse, we can, for instance, start with the definition of the second Stirling number, change basis, but then change basis again. Use the definition of the first Stirling number. Include, after some manipulation of the sum, that we have some inversion formula that says that summed product of the first and second kind Stirling numbers satisfies some equation which tells us that this transform first and second change of basis are inverses. So this has to be 1 for n is L by this equation, and it has to be 0 and is different from L. This is some relation between the first and the second kind Stirling numbers. Now, a second definition, which one can also often find of these Stirling numbers, and which perhaps is more manifestly combinatorial, is the following. So for the first kind Stirling numbers, we will say that the absolute value of these numbers, we'll denote it as kn. This is the number of ways to divide a set of n elements into a cycles. By a cycle, we mean an ordered list of these elements, but the cyclic order doesn't matter. So for instance, if we have element 1, element 2, element 3, this cycle would be the same as element 3, element 1, element 2. So these we count as the same. Very good. And then we can ask, what is the relation between definition 1 and definition 2a of the first Stirling numbers? We'll just prove that they satisfy the same recursion relation. And from there, we could prove that they are the same. How do we do that? Well, we ask in the combinatorial way, we ask, suppose I want to divide an element, a set with n plus 1 elements into case cycles. But one thing I could do is I could take n elements, divide them into k minus 1 cycles, and then add the n plus first element as a new cycle. The other possibility, if we don't want to add a new cycle, is to pick a spot. So first we divide n elements into k cycles, and then we pick a spot anywhere in this list of case cycles. We just pick a random spot of which there are n to insert our a plus n plus first element. So there are n spots. To do that, we had k out of n choices in the first place for these cycles. So we have n times this first kind Stirling number is also contributing to the possibilities of dividing a set of n plus 1 elements into k cycles. So either we add a cycle with the n plus first element, or we add the n plus first element to one of the cycles we had. So this is the recursion relation according to the combinatorial definition. Now we want to see whether this recursion relation is also satisfied from the perspective of the change of basis. So for that, we just write that xn plus 1, by definition, this was the sum of the first kind Stirling numbers. Okay. This was by definition, but also by definition, this is equal to xn times x minus n. So this is nothing but sum k equals 0 to n of Sn k, again by definition, times x minus n times the same thing so from these equations we can decide that S n plus 1 comma k, after shifting this k variable by minus 1, we find that this is also satisfying the same recursion relation. Where the sign has to be adjusted. So we see this recursion relation is the same as this recursion relation. Moreover, we should note that if we sum all Stirling numbers from 0 to n, we will find that this is equal to n factorial, because it is like counting all permutations in the symmetric group. Called Sn. Now we move to the second definition of the Stirling numbers of the second kind. So we also have a second notation for it with curly brackets, and it is the number of ways one can partition a set of n elements into k non-empty subsets. So let's see. Again, we will prove that these numbers satisfy a recursion relation, which we'll prove in two ways using our two definitions, thus suggesting that these definitions are the same. So combinatorially, first, what are the partitions into k subsets of a set of n plus 1 elements? Well, I can partition n elements into k minus 1 subsets and then add a singleton. Or I can add the n plus first element to one out of the k subsets I have. So this would be, I choose k out of n, I have k subsets, but I add the singleton to one of those k subsets. Add to existing subset. There we go. So this is the recursion relation for the Stirling numbers of the second kind. We want to now show this using the definition. So what do we have? We have x to the n, sum k0 n, well actually n to the s plus 1, and to the x to the n plus 1, n plus 1, k to following factorial k. So this is, of course, nothing but x to the n times x. So therefore, this is also following expression, but now times x, right? So therefore, now we want to split x into x minus n plus n. So this is sum k0 to n s2 k x to the k plus 1. Or rather, I should do this in terms of k, of course. So x to the k plus 1. Very good. Plus sum k0 n k times s2 n comma k. And then again, shifting the summation over k and checking that everything is well at the ends of the range, which it is, with the proper definition of these numbers. One finds that s2 n plus 1 k is s2 n k minus 1 plus k s2 nk, which is indeed the recursion relation that we had before using the combinatorial definition. This was using the polynomial definition. Finally, we want to remark that if we sum over all possible ways to divide a subset of n elements, sorry, a set of n elements into k subsets, which are mutually non-intersecting, we will find that we have the total number of ways to partition a set, which is called the Bell number. So the sum of the second kind Stirling numbers is the Bell number. So these Stirling numbers are useful for counting labeled objects with or without repetition, and for forming a Stirling transform on given series of numbers, and they appear often in practical combinatorial problems.